Hello, this is Jason McComb at Oregon Institute of Technology, and this is my final project presentation for EE325 Electronics 3. My project is a DC motor controller design, and the motivation for this project is to come up with a controller to control this DC motor here that you see to the left, and I will show you a live version of this actually. Here is the DC motor. It is let's focus in. It is a 120 volt DC motor rated to 19 kilowatts continuous. It's approximately 16 inches long and 9 inches in diameter. And this is for an electric vehicle application. So my controller uses the control method of pulse width modulation to vary the speed of the motor. And the brains of this operation comes from a microcontroller, which takes in an analog input signal from the throttle or potentiometer and outputs a pulse width modulation signal to control the speed of the motor. And under the hardware design here, I have a flow diagram that kind of illustrates what I'm talking about. Input to the microcontroller, pulse width modulation signal comes out, goes through a preamplifier, goes to the power stage, and then onto the motor. And here I have a picture of the schematic. Let me try to zoom in on this so we can get a better picture of it. There, hopefully that's better and you can see the schematic a little bit better. So this controller is split up into two sections. We have the logic control section here and the power section here. The power section is powered by a 120 volt source. We have power MOSFETs and freewheel diodes for this motor. So when these power MOSFETs are all turned off and the motor's still turning, there is a path for the current to return back through the motor, so it doesn't damage any of the components. And in this logic control section, schematic, we have a 12 volt source, which is a typical automotive battery, and it goes through a voltage regulator to regulate that down to a 5 volt source for the microcontroller here. And it just shows the throttle input going to the microcontroller. The pulse width modulation signal comes out, goes to the FET driver to drive the power MOSFETs which are in parallel there. And this will be implemented on a PCB, and this will have to be separate construction using a larger copper bars that will handle the larger power. If I implemented this on a PCB, it would just melt everything. So because this has quite a bit of power going through it. And that schematic design is based on a design that I found for an electric golf cart. And I've changed the components to suit my needs for an electric vehicle application, namely changing the power MOSFETs and adding more in parallel to handle a higher power capability. And also I've chosen the Atmega 328P microcontroller. That's just something I'm more familiar with, and it gives me more capabilities that I'll discuss later in the presentation. The logic control section, as I said before, will be implemented on a PCB, and here's the PCB layout that I designed in DipTrace. And I also use DipTrace to design the schematic that you see above there. For the power section, I've chosen these MOSFETs here for the power MOSFETs. They are IXFN140N20P. And scrolling through the data sheet, let's see if I can do this one hand. It's rated at 200 volts and 115 amps continuous. And if I need more, I can just add more in parallel. Power dissipation is 680 watts, and maximum operating temperature is 175 degrees C, which I think is suitable for this application. So this is the top contender for that. For the logic control section, and to control the pulse width modulation signal, I had to write code for the Arduino, or I used Arduino IDE in the software design section here. And I will demonstrate the functionality of this code now. And I built a test circuit to do that. And I'm using an Arduino Uno. And this is a simple test circuit. It's not the circuit above. I don't have all the components available right now. So I have the potentiometer. Then here is a MOSFET. Let's see here, which lots of wires going on around here. So we have the pulse width modulation signal coming out of the microcontroller that drives the gate of this MOSFET here. The signal coming from the throttle or potentiometer goes into pin A0. Then we have a very small DC motor here powered by a separate source, which is two 18650s in series, giving me approximately 8 volts. So I already have everything set up, and I also have an analog discovery hooked up for a oscilloscope. So all I'm going to do is vary this potentiometer, and we're going to see the pulse width modulation result output. So I'm turning on, there's the motor turning on right there. I'm actually going to unplug this motor because it's quite obnoxious. And we're just going to monitor the pulse width based on, so the pulse width is obviously in orange, and the input signal from the potentiometer is in blue. And as I vary this potentiometer, we can see the pulse width change correspondingly to the input. If I put it about 2.5 volts, we are at a 50% duty cycle. And the range here is 0 to 5 volts. And so a 2.5 volt input corresponds to a 50% duty cycle, and 3.75 volts corresponds to 75%, and so on. So it's just stepped in increments, and as you do that, the pulse width modulation varies accordingly, like so. So that is pretty much the design of this controller. Additional or future improvements to this circuit would include adding on a bank of capacitors between the high power voltage source and the rest of the power section to provide ripple current and smooth out the power flow through here for a smoother controller. And also, the reason why I chose the 328 or the Atmega 328P is that I can add on more capability, or I can take advantage of the more capabilities of, say, temperature sensing, current sensing. I can monitor the speed of the motor, and I can monitor the voltage of the supply as well, and make decisions based on that feedback. And that's something that I can do in future improvements to this prototype design. That's pretty much it. So thank you for watching.